Okay, the recording has started, and let us start with our lecture as well. First of all, of course, welcome to all of you all for the first lecture of the second semester. I understand your practicals are still on, so and of course, the examinations for the first semester practicals are still to be conducted. Um Not very sure whether they would be conducted here or you would have a combined practical at the end of the second semester for both the semesters as such. But in let me tell you all that these have been very difficult conditions, and in spite of the fact of various difficulties that we faced, we have successfully completed one semester, and we have in fact appeared for our exam also. Of course, the exams, if they would have been offline and of course in a subjective mode, would have brought out the best of you all. But then, since the conditions were such, we were supposed to be conducting it online. And secondly, the fact that it was an MCQ based. As far as geography was concerned, we tried to pose you questions which actually could test more of your analytical skills rather than informative skills as such. And as far as the internal submissions were concerned, I see a lot of students have done well as far as their internal submissions are concerned, but a significant number of them are not seen to have submitted it, though they are on the classroom as such. I don't know what exactly the reasons could have been. And we need to go into an analytical session as far as how you should be making up your presentation as well. While I search for documentaries which we could again be using as a basis for our internals for the second term, uh, compared to other classes, I would rather say particularly school level classes, we would say that we were better placed, that we could interact. Yes, there are students who had difficulties as far as net and connectivity, etc., is concerned, but happy to say that a larger chunk of us have not missed. Yes, of course, all of us are missing college as such, but then we have not missed a significant part of an academics, particularly when we compare it to what has been happening at school level as such. Yes, we are missing the practicals. Yes, being science students, practical happens to be an hands-on part of what we are doing in theory as such. Unfortunately, we have not been able to undertake that hands-on aspect of our learning as such. Possibly, um, we could take it up once we are on an offline mode. However, given the conditions around us to date, it seems difficult for the next couple of months as far as going offline is concerned. But nevertheless, let us continue with the syllabus. Yes, we finished the geomorphology part of the Earth, physical geography in the first semester. And as far as the second semester is concerned, we are supposed to be doing the atmosphere and the oceanographic part as such. I would like to share a few things. Okay, this is what we would be doing as a part of it. Now, let me tell you that while we have done atmosphere for, while we have done geomorphology for a full semester as such, what could be the reasons that we are doing atmosphere and oceanography both put together in this particular semester? Because looking at the larger scenario, I'll just give me some moments and I'll just pin it up on on the screen for you all. Yeah, this is, I've pinned it, and then let me move back. Yeah, an obvious question would be that if why is it that we are doing atmosphere and oceanography together? Uh, at the outset, let me tell you that we did the whole thing in one semester last. That's geosphere or the lithosphere or geomorphology as such, and that we are putting these two spheres together does not demean at at any point of time of our study the importance of these two. The fact that we do geomorphology more is basically because man is a land animal, and we need to understand, as animals on land, we need to understand what is happening on the land, for the land, around the land, with the land, and so on and so forth. So the details of it were so much enough for us to uh, comply to the whole semester as such. And let me tell you that as far as atmosphere and oceanography is concerned, at a higher scale, that's at a postgraduate level, you will find that climatology is a separate paper and oceanography too is a separate paper in itself. Given the fact that we were supposed to introduce ourselves with these things, it becomes necessary that we uh, put it together. Now, see, this is a year wherein we need to put it. First year is basically divided into 2 semesters, so we should have had time to all the three of these spheres separately. But then, as I said, given the scope of that particular sphere, as such, we did the geomorphology for the first sem, and then we are going to combine atmosphere and oceanography together in the second sem as for our study. And let me tell you that we are going to complete and comply to all the basic things that we would be requiring as far as atmosphere and the hydrosphere is concerned, as such, because I repeat, all of them are equally important. Okay, there is nothing that we need to skip off these, but then the structure of the syllabus is such that we had to cut down on something, and of course we had to do a bit of it in detail, a bit of the other in detail as such. Before we come to the atmosphere, I am sure you have done well as far as your uh, MCQs are concerned. Given the type of presentations or submissions that I had, I could vouch for the fact that majority of the students, I won't say all, but majority of the students showed keen interest in the study of the subject, and which was quite evident from the fact that we had very good submissions as such. Yes, some were not up to the mark, and you'll realize that when I had posted the marks out of 15 for y'all, some of them did not do well as far as the out of 5 marks for the assignments were concerned as such. Anyway, coming back to the fact, what all we have done in the first semester is in front of you. As far as one single slide is concerned, I would excuse you all, I would ask you all to excuse me to basically don't read into this part. I'm coming to what exactly that means, but I did not have space, and that's why I've pasted them here. What these are, I'll come to it later. But then, going back to and revising what we have been doing for the last semester as such, we were doing the geomorphic processes as such, which included terrestrial processes and extraterrestrial processes. Terrestrial processes basically mean everything that happens with the Earth. Extraterrestrial means something that comes beyond the Earth as such. Now, this could include, say, activities like sunspot activities. You'll see that those of who would connect to the term sunspot activities, those who are from physics would certainly know this. And it is a known fact that sunspot activities do have their impact on activities on the terrestrial processes as such. Then other extraterrestrial things could include the say the um, path that the Earth takes around the sun. At times it is circular, at times it is elliptical, at times it is planar, at times this plane is tilted, and all of this leads to what is called as climate change, as per what Milankovitch has said, and we have done this in the Milankovitch cycles as such. Geomorphology, because it's related to land, of course, exclusively includes terrestrial processes. We have done terrestrial processes, which are further divided into exogenetic and endogenetic as such. Endogenetic, of course, we mixed it because there is no superiority or inferiority as far as doing these processes is concerned. It is a matter of convenience where we start and where we end. Endo, the word means everything that comes from within the earth as such, and thus you'll see that endogenic processes were further divided into very fast affecting processes as such. and very slow affecting processes as such. Okay, fast affecting or sudden movements, as we call them, are called as examples being volcanoes and earthquakes as such. And then you had diastrophism, and of course we had folding and faulting, and we had orogeny, which is mountain building. Mountain building may again lead to folding and faulting as such. And while mountain building is at a local level, you could have these very things happening at a global scale also. So all that was done in endogenic processes as such. And as far as exogenic processes are concerned, you'll see that the driving force of this is going to be the sun as such. Now, an immediate question from your side could be, sir, isn't the sun an extraterrestrial object as such? And then how could you relate these things to exogenic processes? My answer to this would be that the energy from the sun does not directly impact processes on the surface. It is helped by the processes which happen within the atmospheric layers. And here is where the atmosphere comes into question. As such, of the various layers of the atmosphere, we have the lowermost and the most dense of these layers, called as the troposphere, is where this energy gets trapped, and it is within this layer that the change and exchange of things happen. I'm going to introduce these aspects from in some period of time from now. But then all these are called as agents, processes of denudation, and which would include weathering, which would further include physical, chemical, and biological weathering. We have already done that. We include erosion and transportation of material through various agents of erosion, and we said that from river to glacier, and from groundwater to uh, waves and tides, and of course eventually wind erosion. All of them lead to deposition, aggradation, and various types of um, features that form out of this. And add to all of this mass movement, which is a direct impact of gravity that happens with regards all these things on the surface of the planet, of the lithosphere particularly, is concerned as such. Coming to the right side as such, the origin of it is all of it is magma. It solidifies into rocks, and then tectonic processes will include folding, faulting, tectonic upliftment, and all such things formed out of folding, faulting, tectonic upliftment, layered subsistence are called as structural landforms. A meander will not be a structural landform. A mountain, however, will be a structural landform, and a fault is going to be a structural landform. A rift valley is going to be a structural landform. Okay, so we have to understand the differences between various landforms. And in this process, we identified various types of rocks and how they are formed. And eventually, we went further to identify the weathering out of this. And you'll see that the weathering landforms include soils, various types of soils. We include karst, caves, etc. in weathering landforms. As such, it is basically, if you remember, the decomposition and disintegration of rocks and minerals by physical and chemical processes. In fact, it is these physical and chemical processes which further yield us physical weathering and chemical weathering as subtypes of them. Okay, and all this leads to what is called as debris. Okay, and then we have sediment erosion, detachment of transport of material by wind, water, and ice, and these are called as erosional landform. These are called as erosional landforms. And what is eroded from one point is, of course, carried as load, and it is going to be deposited somewhere. And this deposition takes place with wind, water, and ice into consideration. All these are called as depositional landform. Alluvial fans, deltas, floodplains are example of this. So anybody who's looking into further studies of geomorphology, let me assure you that the whole of geomorphology is in front of you, minus this particular thing. Okay, and let me assure you that once you have understood the processes in which you can see in front of you, understanding the detailed processes of geomorphology would not be much a difficult thing as a process. Now, maybe this brings in memories of what we had done in the first semester, all those topics that we did around geomorphology and geomorphic processes. And thus, that brings us to atmosphere. Now, obviously, another question possibly could from your side could be that why is it that we take atmosphere? Why is it that we don't take oceanography to start with? As I said, that there is no sequencing, particularly with regards to the importance of these topics. I would say the atmosphere would have more connection as compared to oceanography, and possibly the reason why we are taking atmosphere immediately to follow the studies of lithosphere and geomorphology. And this is because of the fact that if you remember, exogenic processes are an output of the energy from the sun, which is spread in the lower layers of the atmosphere. This, I would say, is enough a connection to go into the details of the atmosphere and the studies of atmosphere, which says that it is nothing but it's an envelope of various gases. Now you'll see that interestingly, the word life-giving gases is written here. An obvious question that would render into your minds is that is the whole atmosphere a life-giving, an envelope of life-giving gases, or is it oxygen, which is the only gas which is important for us? Okay, could obviously be a question for a curious mind. Let me tell you, and of course, we are going to go into the details of that, that every gas, and in its right percentage, is going to be of equal importance to us. And it's not only oxygen as such. Okay, 100% of oxygen would certainly not have served the purpose of life on this particular planet, because just like oxygen has its positives, you'll see that oxygen has its negatives, particularly oxidation as a process, the most common process that we see happening around us, if you remember when we spoke about chemical weathering. Okay, so slowly now you'll very frequently hear me relating a lot of geomorphology in atmosphere also. I did not do so in geomorphology because we were introducing us to that particular subject for a fresh on a fresh canvas, and as a consequence, now that we have geomorphology at the back of our minds, we have studied it in the first semester, and now we are going into atmosphere. I would try to at points wherever required and necessary, connect these things to each other, so that eventually you remember that diagram that we spoke about, the three spheres: atmosphere, lithosphere, and hydrosphere, and in between them the gray area on which we had the biosphere. So atmosphere becomes equally important, and the study of it is equally important as such. And as far as the importance of these gases are concerned, I've just said that uh, as students of chemistry and as students of physics, you could just imagine a hypothetical condition if instead of 21% of oxygen, we should have had 20 or 21%, however you may consider it. But had we had 100% of oxygen, would it be beneficial? Would it be not beneficial? And would it be harmful? Or what exactly would have been the scenario around us? You can just give it a thought. Okay, so when compared to the thickness of the radii or the radius of solid Earth, which is around 6,400 kilometers, the atmosphere comparatively is very shallow. And in fact, the active part of the atmosphere is even very shallow. As there are still, I would say, difference of opinions as far as what should be called as, um, so to say, the exterior limit of the atmosphere, because there are huge difference of opinions when it comes to actually considering the outer limit of the atmosphere. Some scientists say that it is only 100 kilometers. Some scientists say that it's going to be a few hundreds of kilometers, while others say that or we should be considering the extent of atmosphere to the point wherein we have even a trace, even a minutest of the trace of any of the elements that we find near the surface of this planet. And accordingly, they say that this could run into at least 29,000 kilometers. Uh, and thus, you'll see that, however, we know that as far as the active part of the oxygen of the atmosphere is concerned is more near to the surface, and that is to do with gravity. And I think I did speak to you about gravity. Yeah, this thing that I had in my mind when I was in school, when I happened to learn gravity for the first day of time, and I think I over understood gravity as a concept as a student of science, or I would say I understood or I underestimated the importance of gravity. There could be a discussion about it. But then when my teacher said that the Earth is rotating and revolving around Sun, and this is big, and along with this you have these solid and liquid cores which lead to the whole aspect of gravity, and gravity holds everything to the surface. And having said that, she also said that the speed at which the Earth rotates along the equator is the maximum, and within 24 hours, you would be traveling 44,000 kilometers. Sorry, that is the circumference along the equator as such. And a thought came to my mind that, okay, if the Earth is going to move at that particular speed, and if I was able to jump and be in the air for a significant period of time, I would not be requiring transportation, because the moment I jump away from the surface, the Earth beneath me would obviously be rotating at a significant speed, and by that time I would have traveled a significant distance without any personal effort. However, later I realized that it's not that way, and everything in the force of gravity moves along with that. And in fact, gravity, the rotation, all of this is going to have an impact which we later studied as Coriolis force, and we are going to do Coriolis force in this semester as well. And the fact that the very life and of course the hypothetical condition wherein I imagine that if we are minus gravity, what would happen, and I would imagine myself floating into the air. But at a later point of time in my school itself, I realized that gravity not only holds everything, it holds the atmosphere also. And without gravity, it would be very difficult for us to even breathe for a few minutes, if not few seconds overall. And having said this, we should underline the fact that 99% of the atmosphere is within the first 30 kilometers. Okay, so if this is 28, 29, 30, so this is would be 30, and you'll see that if we are to consider this part as the pressure part, okay, air pressure as such, you'll see that the normal air pressure is somewhere around 1018 millibars or hectopascal, however you may be considering it. But you'll see that when you go away from the surface of the Earth, there is a decrease as far as the atmospheric pressure is concerned. You'll see that up to the first 5 kilometers, you have already dropped down to 50%. Okay, so you'll see that first 5 kilometers has more than 50% of the total atmosphere, beyond which you'll see that it takes a very sharp turn, and you'll see that within the next 25 kilometers, it drops by another 49%. And you'll see that by the 30th of kilometer, we have less than 0.01 atmosphere left beyond this particular point. And that is why the argument, as I said, that what should be the exact limit of the atmosphere. And another reason that you'll see that when you're climbing the Everest, at this point here, when you're summiting the Everest, you'll see that most of the climbers will be using oxygen cylinders along with them. And you'll see that climbing the Mount Everest without oxygen is also considered to be a tremendous feat, basically because of the fact that the pressure is very, very low. It's just 314 millibars as compared to 1,000 millibars around 8.5 kilometers down onto the surface. Okay, all this has to play an important role in the understanding and the study of the atmosphere. Why is the atmosphere in discussion more so? A very common term nowadays being studied in what is called as climate change. Okay, and because of all these things happening around us, and why is it that we refer to the atmosphere more? Because in context of climate change is because of the fact that invariably, because it's in a gaseous state, it's very dynamic, and because of this dynamism, you'll see that it happens to be the first of the spheres to be affected the most. But let me tell you that when it comes to dilution also, it is going to be the first of the spheres. And that's why nowadays the present concentration on atmosphere is huge. And that is why we study about the atmosphere much in detail nowadays. It's being affected very fast. Not that the others are not, but you'll see that the rate at which water is going to be affected, the rate at which land is going to be affected is uh, going by the physics of these three. The the solid part is going to be affected the latest, and then the liquid part. Of course, the fastest one to be affected is going to be the gaseous part, which is in the part of the atmosphere. Okay, so before we go any further, okay, to arouse our interest in these things, uh, I will just come to a few things that we are supposed to be doing. And in that context, I have the three links that I had pasted on that particular slide are nothing but YouTube links, and we would be looking into these links one by one. The first one, of course, why do we study climate? Why has it become necessary to study climate as such? Okay, so let us now first let me pin it, and let us now start and try and understand what exactly is this whole issue about climate science.
Let's not beat around the rapidly melting iceberg here. Climate change is happening, and we are causing it. The evidence is overwhelming. Scientists usually reserve this level of agreement for claims like Earth is a planet or air is real. Yet here we are. The climate change ship has now left the dock, yet lots of people on shore are still debating whether boats can actually float. But maybe you're a person who trusts and accepts what climate scientists are telling us. It's just sometimes it's hard to explain why. I mean, we've all been there. I care about the environment. I figure with the polar bears and everything, we might as well try electric cars. What do we have to lose? And then they go caps lock serious, saying they have proof that climate change is a hoax perpetuated by scientists paid off by the polar bear lobby as part of a plan to install Al Gore as Supreme World Polar Bear Emperor. Wake up, sheeple. To keep that from happening, we put together this handy reference. The sun is the source of warmth on Earth, so thanks for that, sun. Ice and clouds reflect some of its light away, but the rest is absorbed by land and water and re-emitted as heat. Some of that heat escapes to space, and some is held in by the atmospheric greenhouse effect. The insulating effect of Earth's greenhouse gases are the reason that life exists as we know it, but human activities have increased the concentration of one of them, carbon dioxide, 40% since the Industrial Revolution. We know the sun's output has varied during history, but since the 1970s, the period when global temperatures increased the fastest, temperature and solar activity have moved in opposite directions. If the sun was to blame, it would cook the upper and lower layers of the atmosphere together. Instead, we only see warming in the lower layers, the same place that human greenhouse gases like carbon dioxide are piling up. Since 1870, with fossil fuels, cement production, and land use combined, humans have put about 2,000 gigatons of CO2 into the atmosphere. That's 2 million tons, and about 40% has stayed there. Studying gases trapped in ice cores has let us see what Earth's atmosphere was like in the past. At more than 400 parts per million, today's carbon dioxide levels are the highest they've been for almost a million years. That's before humans even existed. Totally uncharted territory for us. More carbon dioxide in the atmosphere means average temperatures across the globe are increasing, and fast. Right now, Earth is warming about 10 times faster than at the end of an ice age. Okay, so CO2 is increasing. How do we know it's our fault? The best evidence comes from looking at what isotopes, or different kinds of carbon, are in the atmosphere. Fossil fuels come mainly from old plants. Plants prefer to use the lighter isotope carbon-12 over the heavier carbon-13, so they contain a higher ratio of 12 to 13 than the atmosphere does. When more fossil fuels get burned, the percentage of carbon-12 in the atmosphere should go up, and that's exactly what we see. And it's not because of volcanic activity. Volcanoes only emit about 1% as much CO2 as we do. Normally that CO2 is balanced in exchange between the atmosphere, plants, and animals, but eliminating carbon sinks has released centuries worth in just a few years. Other greenhouse gases are also increasing, like methane from farm animals and natural gas processing, or nitrous oxide from fertilizers. If we run simulations just using natural causes of climate change, they predict no change or even cooling in the 20th century, and that is not what's happening. It's still going to get cold in some places, but in the 2000s, there were twice as many record highs as record lows. And each of the past 3 decades has been warmer than any other decade since we started measuring in 1850. Since 1900, actual temperatures around the world have increased almost a full degree, and most of that has happened since the 1970s. Looking at data from tree rings and ice cores, the past 30 years is probably the warmest in 8 centuries. Of course, not every place on Earth warms equally. Oceans cover more than 70% of Earth, and they absorb more than 90% of the heat added to the planet. Naturally, that's where we see the most extreme changes. Around the world, oceans are rising 1/10 of an inch per year, and they're up 8 inches since 1901. This is because water expands as it warms. And when ice sheets and glaciers melt in Greenland and Antarctica, water that's normally on frozen land gets put in the ocean. The oceans are Earth's largest carbon sink. As more CO2 enters the atmosphere, more of it dissolves in the ocean, which makes the water more acidic. This doesn't mean the oceans will be made of acid, but animals with calcium shells are super sensitive to pH. We're on course for the oceans to hit pH 7.8 in 100 years, which could wipe out 1/3 of species in the ocean. We also know that levels of summer sea ice in the Arctic have decreased 40% since 1978. They might be the lowest levels in 1,400 years. That white sea ice usually reflects the sun's energy back into the atmosphere, but the dark ocean is soaking it up like a black shirt on a sunny day, which feeds the cycle forward. If CO2 emissions continue on their current trends, Earth is on course to be 2.5 to 5 degrees warmer. The oceans could be up to 1 meter higher by the end of this century. Is that a big deal? Yeah, it's the biggest deal. This is by far the greatest issue facing our species. The last time the Earth averaged a few degrees colder, most of North America was covered in a mile-thick sheet of ice. That many degrees warmer? We're gonna have a bad time. So now you're armed with the facts, why we know climate change is happening and why we're causing it. Please, share this information with the people you know, and then let me know. Did it change any minds? Did it change your mind? I mean, are facts enough? If not, then why do so many people continue to not believe in climate science? We'll answer that question in our next video. Stay curious.
If you wish to make curiosity from scratch, you must first invent the universe.
Okay, that in fact, those 25 reasons I think has given me an idea as to these things could also be the next topics of our assignments. Okay, because going back to the assignments in the first semester, though some of them, and when I say some, around 15 to 20% of them were very good, but 80% of them, I should say, were very, very general, and they seemed to be a continuation of what you had done as your assignments for 11th and 12th environmental studies. Okay, this gentleman here was very serious about putting up those 25 things about why we should be worrying about climate change. And as students of science and studying geography and now studying climate as a part of it, we should be going into a bit of details. I would, and in this semester particularly, be expecting you to go into researching a bit, because as I said, majority of the presentations were cut paste of one particular. They looked into one particular idea, and then of course you had 3 topics, but what most of y'all did was you just took up one each of those topics, a larger content of this was found on the net, and then you just copied a few things from there and pasted it, okay, into your assignment. What would be expected here now is that we should be going into a bit of details. That means we should always have at least some part which is convincingly new to the audience. Of course, this is not the time that I am right away announcing these assignments, as but just a thought that we should be thinking on these lines also. Going back to what this person was saying about this, you can of course revisit it by using those links that I have posted in the slide, okay, which would be available as a part of this recording. And I'm going to come up with a few more things. But then there still are a few things which at times uh, I don't know why people at times underplay climate change, and at the same time some people are overplaying climate change. So, for example, one statement that this particular gentleman was making is that the temperatures are the rate of increase of temperature is many times, I don't recollect how many times, but many times higher than at the end of the ice age. I think this was the 16th or the 17th point. Now, let me tell you that there is something which is called as a lag. Now, what is a lag? You see that when we spoke about geography in the initial lectures, and we said that the solstices happen on a particular date, and the say the equinoxes happen on a particular date. I've been mentioning it in our WhatsApp group also, that though as far as we understand equinox is concerned, uh, it should be on what, the 23rd of 21st of March, or the 22nd or 21st of June. March, April, May, June. No, no, sorry. September and March. And what does an equinox mean? A 12 hours day and 12 hours night. However, you'll see that if you go through the sunrise and sunset at various places on the globe, you'll see that it exactly doesn't match. One. Secondly, if the summer solstice and the winter solstice happen to be on December and what, July? Sorry, June and December, they should have been the hottest day and hottest night and coldest nights respectively in the respective hemispheres. Now let me tell you that as far as with particular reference to December as such, the lowest temperatures in the northern hemisphere are not around 23rd of December. Rather, you'll see that they happen in Jan, say the first or second week of Jan. Why this happens is basically the happening on 23rd of December to take effect from the sun into the atmosphere, from the atmosphere to the surface, from the surface back to the atmosphere is obviously going to take time. And this take of time is going to be called as a lag. So if we apply those logics there, it's not very convincing to say that the temperatures or the temperatures rise during the age, during the end of the ice age was much slower than what it is happening. No doubt it is happening, and 99% of this is happening with regards our human induced contributions. And of course, he has listed so many things that we contribute to. And while he also says that while some people would crib about the fact that volcanoes do emit carbon dioxide, the percentage of carbon dioxide emitted is obviously much less than what we are actually emitting out as anthropogenic activities, I would say. Another fact that should fascinate us to study atmosphere is basically the dynamism of it, how dynamic the whole issues in the atmosphere are. And you'll see that I found this clip on the YouTube, which is so very intriguing and so very beautiful to look at. And when we go through it, it just fills our mind with pleasure and, of course, a lot of curiosity and the intensity with which we should study climatology and, of course, atmosphere to as such. So let us now play that particular this. You just see the beauty of the atmosphere here.
Sir, you are not audible.
Sorry, yeah, thank you. That's so very fascinating and amazing, and of course, so many things yet to be learned about the atmosphere, which we saw about in the earlier part, and of course, in the later part, the rate at which we are polluting the atmosphere. We need to arrest it. We are trying to. Governments are trying to, but a thing very similar to Corona. You'll see that only a few people are trying to make an effect, while majority of them are not caring about it. Is something which is very unfortunate, which is happening with majority of the unfortunate things around us. As a consequence, the more we study about it, the more we would be able to tell about the adverse effects to people around us. And as a consequence, this should help us in a better understanding uh, post the study, of course, in this whole process. A few more clips remain, but since we are nearing the end of the time, and I don't want to bore you all to the whole length of the lecture. Um, this is just an introduction into what we are you should be expecting. Everything that happens around the atmosphere, right from the layers of the atmosphere, will come down to the lowest of the layers, and that's the troposphere. As the troposphere is always is many a times referred to as a theater stage, okay, like by many, in the sense it's called as the theater stage basically because it changes curtains so very frequently and so very regularly. You must have seen a few of them in the earlier part also. In the clip, sorry, the various colors and the dynamism of the atmosphere that's within, and all of this happens within the first 10 kilometers from the surface. So it's going to be very interesting to study this part, this layer particularly, the troposphere, after having learned the various gases, the importance of each of these gases, and not only oxygen. And of course, then we'll be coming to how the troposphere behaves in different temperatures, leading to different pressures, and how different pressures lead to different types of winds, and eventually how all of this is going to have an impact on the lives around us. Okay, let's see how far we can go. If you have any questions for me, I'm ready for those questions. Anything that with regards anything that we have done to date. I'll just wait for your questions for a couple of minutes. If you don't have any questions for me, then let us call it a day. I'm stopping the recording now.